Okay. Turn off the air conditioning. Anyway, welcome back. Chapter 7, Video 2. And here's your teacher to think of. And I picked this guy because he's pointing at aluminum. And I love teachers who point when you don't understand something. You ever have a teacher like point and then you don't understand, so they kind of like circle it, and then if you still don't understand, they circle it more, and then they start like hitting it with the like thing they're pointing with. Anyway, so this guy, dude, that's so fake looking. But anyway, moving on. Start two concepts here. One, molecular versus structural formula. And then we'll take a look at how to do atom inventories for mass calculations later and for analysis. And I'm going to go ahead and throw in molecular formula versus empirical because it kind of relates here and it makes sense to do so. All right, so what is the difference between a molecular structure or a molecular formula and a structural formula? And hey, you can go to the internet and you can steal a slideshow from another teacher like this. Look what we got. All right, so molecular formula gives you two pieces of information. If we take a look at that molecular formula, we know two things. We know the atoms that are involved. We know that there's carbon atoms and there's some hydrogen atoms. If we look this up, if you don't already know, H means hydrogen and C means carbon, you could look it up. And that's why you have your periodic table there, right? And O means oxygen. And we know from doing this stuff in middle school that there are two carbon atoms and that there are 6 hydrogen atoms and there's 1 atom of oxygen. So we know the ratio of atoms, and we know the total number of atoms in that material, and we also know which atoms are involved, so the number and types of atoms. Now, a structural formula tells you the same thing. However, a structural formula gives you more information. In other words, a molecular formula may not always be enough of the information. For instance, there are things called isomers that we're going to study in chapter 13, and that'll be in the third, I'm going to call it the third marking period of this course, where you have two things that have the same formula, C2H6O, and you get two different compounds. This first one is called dimethyl ether, and the IUPAC name for this is methoxymethane, and ethers are solvents, and this is something called ethanol. And ethanol is a dehydrating agent. Or you can distill it and make beer, wine, and all that other kind of stuff out of it. And this is methoxymethane. Now they function as two different types of materials, even though they have the same number of atoms and they have the same types of atoms, C2H6O. But the difference is the way they're connected. And we'll find out what this means when the oxygen is connected in the middle versus the oxygen being connected more towards what they call the terminal end of it. So structural formula is going to tell you the connectivity, how things are brought together. Now, there's a number of different structural formulas that we're going to use in this course. All of them are kind of generically called skeletal structure. And if they include the little dots, like we had in methoxymethane and ethanol, if they include the little dots, they're called Lewis. Technically, this isn't a Lewis structure, though. What they showed here in the example is something called a Kekulé structure, something I use in organic chemistry. So that's one type of structural formula we'll use. If we go back to this example and we zoom in, they're actually using something called a condensed structure or condensed structural formula. So with a condensed structural formula, there's nothing condensed about it. For instance, let's say we have a compound like hexane, and hexane has the formula C6H14. Now, the skeletal structure for that would be, I'm going to do the skeletal structure in green, would be a carbon connected to another carbon, 6 carbons connected in a straight row. Well, they're not really straight row, they're tetrahedral, but how about 6 carbons connected in a row? And then we'll go 1, 2, 3, 4, 5, 6 hydrogens on each side, north and south, and a hydrogen on the east side, a hydrogen on the west side, and that would be the skeletal structure of hexane. So in a condensed structure, what they do is, because in organic chemistry, carbon is so important, we're just going to focus on what's on each carbon. So we're going to say that this is CH3, a carbon connected to 3 hydrogens. And here on the next one, we're going to say, all right, this one's connected to 2 hydrogens, so we're going to write CH2. And then we just go through the rest of the carbon chain. CH2, 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 and then on the terminal end, we have CH3. So that would be a condensed structural formula. And you could even shorten that condensed structural formula by writing CH3, now CH2 in parentheses, and then you say how many of those CH groups you have. We have 1, 2, 3, 4 of them, so we're going to put a little subscript 4, and then put another CH3 at the end. So that would be a better condensed structural formula. We're also going to use in this course something called a bond line structure. And in a bond line structure, in organic chemistry, we assume carbons and we could care less about the hydrogen. So if we're drawing hexane with a bond line structure, we just draw these lines. And at each vertice and each endpoint, we assume there's a carbon. So I'm going to write in the assumed carbons, then I'm going to erase them. That there would be a carbon here and here and here and here and here. Oopsie poopsie, that's 5 of them. Hexane has 6, so let's do that. And then our 6th carbon is here at the end. And then they don't even draw in the hydrogens. They assume that you know if you're at an endpoint, there's 3 hydrogens and 2 in the what's called central positions, and then 3 more here at the terminal position. So in organic chemistry, we care about those carbons. We don't care about the hydrogens. And I'll explain why when we do chapter 13, and that's called the bond line structure. So hexane for bond line would be drawn with those zigzags. And then lastly, we're going to do something called dash wedge. And dash wedge structures are used to show 3-dimensional shapes. So for instance, let's say we had a carbon connected to 4 hydrogens. These 4 hydrogens would be at what's called a tetrahedral angle. You don't have to know that yet. We'll do that in chapter 13. And then this little wedge means that there's a hydrogen coming out of the plane towards you, and then another hydrogen on the dash going into the plane away from you. And it's used to show 3-dimensional structure, and we will deal with that in chapter 13. All right, so structural versus molecular. Now, with that said, at the end of the chapter, they talk about empirical versus molecular, so I might as well just do that now because it kind of blends in here. Now, on this thing that I stole from the internet, it gives you some definitions to compare, and I'm going to use this now, but the only thing that we have to focus on is the first definition up here. The rest of the stuff in this we are going to do in chapter 8 when we do analysis of the mole concept in molecular versus empirical. But for now, you just have to know what molecular and empirical is, and to be able to take a molecular formula and turn it into an empirical formula. Now, it says here, empirical is the simplest form of expressing the element in compound. So it's like a fraction. If you have 2/4, you would reduce it to 1/2. That's going to be the simplest form. And in a molecular form, it's the actual number of atoms in that compound. And let me show you how that works. I'll give you an example. Sugar, for instance. Sugars fall into a family of materials called carbohydrates. And the empirical formula for a carbohydrate is CH2O. That's the empirical formula. It's a carbon, there's your carbo, and then H2O, hydrate, like being hydrated by water. CH2O. Now there's a bunch of different types of sugars. If you have C6H12O6, you know from middle school that is a sugar called iodose. No, mannose. No, talose. No, galactose. No, there's actually a whole bunch of these what's called hexose sugars, but the one you know is something called glucose. All right, so we have glucose, H12O6. But when you study DNA and RNA, there's a sugar called ribose, right? Ribose, I can spell it, and like in ribonucleic acid. So ribose sugar, different than glucose sugar, but if you take those formulas and you reduce them down, so we're going to take glucose and we're going to divide each of those by 6, we get C6H2O. If we take ribose and divide each of those by 5, we get CH2O. So you can think of the empirical formula as sort of the family formula. They all come down to this ratio, whereas glucose and ribose represent the individual sugar. So empirical formula for a sugar, CH2O, but glucose has a different formula, ribose has a different formula. Tetros, right? Tetra meaning 4, so you can predict the formula. Go ahead and give it a shot. I'll pause. I'm done. I'm back. So C4, when I say I'll pause, that means you pause and try it, right? Okay, C4H8O4. And again, that reduces down to CH2O, which is the empirical formula. All the rest of this definition from this little thing that I stole from the internet, we're going to go over that in Chapter 8. Sorry, allergies, and they're doing road work on the street, replacing pipes, and there's a tremendous amount of dust, so forgive me for that wheezing and coughing and stuff. I'm just real sensitive to it. And I listened to my first video and I was like, welcome to chemistry. So anyway, last part of this video, atom inventories. Pretty easy. An inventory is a list. And if it's an atom inventory, it's going to be a list of the atoms that you have in that substance. Some of them are pretty easy. All right, so I don't even have to teach you this one. If I did hydrogen phosphate or phosphoric acid, if it was in a liquid, I'd say, all right, what's the atom inventory for this? Well, you would list the types and the number of atoms. So, and you're going to get a lot of practice at this in your recitation, I imagine. So I'm just going to make my list. I got hydrogen atoms. And I got P for phosphorus. If I didn't know that, I would look that up on the periodic table. It's not potassium. Potassium comes from a Latin word, starts with a K. I always forget what the Latin word is, though I care less. Anyway, or is it Greek? Who knows? That instills confidence in your teacher, right? All right, oxygen, and then we just have to write the number of atoms. So we look at this, hydrogen has 3 atoms, so we say 3 hydrogen atoms. And phosphorus, you know, we assume there's a 1 here. They don't write the 1. Like, it's not H2O1. I mean, it's not wrong if you write H2O1 for water. It's just not done. So it's considered bad form. So we leave the 1 out. So there's 1 phosphorus atom, and there's 4 oxygen atoms, and you're like, oh, put a ton of these on the test because they're so easy. And I agree with you. All right, so suppose we had something like this. There are things called polyatomic groups, special groups that we keep together in parentheses. So suppose we had something like this. All right. So we want to make an atom inventory for that. Okay, no problem. We can do that. We look up Cr if we don't know that that's chromium. Again, I'm using our periodic table here. And I know you've seen a periodic table before, which is why I'm not wasting your time with it. Now, as far as the group, what it's saying is we have 3 of that group. That group is something called the nitrate group. And so what you do is you take the 3 and you distribute. It's a little different than algebra, but it's the same sort of concept. We're going to distribute the 3 to each of these individually. So we have nitrogen, and we have oxygen, and there's 1 chromium atom. However, there's 1 times 3. 3 nitrogen atoms, right? And then 3 times 3, why am I saying right? 3 times 3 on the oxygen atoms gives me 9. I just have to write in the word atoms because it's annoying when people don't. It's annoying when people do. Let's try another one. All right, give this one a try. What if we had... What if we tried this one? All right? Ammonium oxalate is what this is called. All right, going to pause here and you try it. Hey, I'm back. So here's the answer. We're going to distribute this to, we're going to distribute it to the nitrogen. We're going to distribute it to the hydrogen. So we have 2 nitrogen atoms. And we have 2 times 4, 8 hydrogen atoms. And then the rest we can do like we normally do, 2 carbons. And finally 4 oxygens. All right, so what if they give us one of these structural formulas? Again, I'm glad you're asking these sort of questions. You're asking all the right questions. Suppose we had CH3, CH2, 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 and then let's put a fluorine here at the end. All right, so what's the atom inventory for that? You just add them up, take the sum of the number of carbons. Just because we separated them in the condensed structure doesn't mean there's any less of them. There's a total of 4 carbons, right? 1, 2, 3, 4. 4 of those carbons. So we're going to write that down. And the hydrogens, we got 3, 5, 7, 9. And 1 little fluorine at the end. And remember, it's not spelled F-L-O, it's F-L-U-O-R. That would be fluorine the other way. 1 fluorine atom. Okay. Another type of compound I should show you is something called a hydrated compound. Now, a hydrated compound is one that is weakly attached to water molecules. And they show this weak attachment by writing a dot, and then they write the number of water molecules, and then they follow it by H2O. So you have a compound, I'm going to call that X, and then a dot, and then the number of H2Os. Let me show you. Suppose you had this. Let's do cobalt sulfate hexahydrate. The way you treat this is you treat this as one big thing, and you distribute this 6 to the water molecule. So this is going to be 1 cobalt atom, 1 sulfur atom. Now the oxygens. All right, I'm going to keep a tab here, because I got oxygens over here on the left side, and then I have some more oxygens over here on the right side. So on the left side, I have 4 of these oxygens. I'm going to write oxygen here. I got 4, plus I have 6 times 1. So 6 in my hydrated part, and that gives me a total of 10. So I actually have 10 oxygen atoms. For the hydrogen, I have 6 times 2. So that's going to give me 12 hydrogens. Yeah, this is where students struggle. They struggle with this hydrated thing. So I'm going to have you try one. What if I gave you this on a test? I said, let's do, I don't know, why am I struggling here? I could do just about anything. I could make stuff up and you wouldn't know. All right, let's do manganese. Dude, it's getting late. That's what's going on, folks. It's getting late around this place. Let's do that. Dot. Nona. That's supposed to be a 9. Nona hydrate. All right. Manganese 5 chlorate. Nona hydrate. That's what that's called. All right. Give this a try and then come back and I'll show you the answer. I'll pause. Hey, I'm back. All right, so I know I got 1 manganese over here. Now, that's not magnesium. Look it up, it's manganese. So 1 manganese. But I'll tell you, some people make such a mistake between magnesium and manganese that on the AP exam, they'll give you half credit if you call that magnesium. I don't think they should give you any credit, but they'll give students half credit. So we have 1 manganese here on the left side, and we have 5 times 1, 5 chlorine atoms on the left side. Now we have oxygens on both sides, so I'm going to save that to the end. We have 9 times 2 on the hydrogens. And then lastly, we have, let's do this in a different color pen. Let's do this in blue. we have 5 times 3 on the oxygens. So again, I'm going to keep my little tab of oxygens over here. That gives me 15 on the left side. And then I got 9 times 1, 9 on the right side. So that gives me 24 oxygens. And then I just have to write in the word atoms, or atom. Okay, one last one. Sometimes they put a coefficient in front of the formula. If they do that, here's what you're going to do. Let's say I have 4 molecules of CH3 COOCl. Okay. What you're going to do is you're going to figure out what's in the molecule first, and then take the whole thing and multiply it by 4. Because it's saying you're going to use 4 of these molecules. So I'm going to figure out what's in the molecule first. In the molecule, I have 2 carbons. That last one is not a carbon. That's C with an L. That's chlorine. So I have 2 carbon atoms. I have 3 hydrogens. And I have 2 oxygens next to each other. Sometimes they write it that way in organic chemistry. And then I have a chlorine at the end. 1 chlorine. And then what I'm going to do, since it has a coefficient of 4, is I'm going to take all of this and I'm going to multiply it by 4. So my answer is going to be 8 carbon atoms. Yeah, I'm telling you how to multiply by 4 here. 12 hydrogen atoms, and if you zoom in, that's like the worst N in the world. And then we'll do 8 oxygens, and 4 chlorines. All right, that's it. That's video 4. Got all this done, ready for the first day of class. Can't wait to see everybody, all 104 of you. All right, have a good night. Thank you.